Apple II wire-by-wire build, the video circuit. I'm Dr. Matt Regan. I'm going to go over the build for the video circuit for the Apple II now, and this may take a number of videos. I'm going to build a breadboard circuit first to demonstrate the principles, but the actual build for the Apple II is quite different. The circuit that I'm ultimately going to use is actually a testbed for the Turing 6502 video circuit. In this video, I'm going to go over some of the basic principles and look at the generation of the horizontal sync signal. Steve Wozniak designed and built the Apple II, and the video circuit is, in my opinion, the trickiest part of the design. Fortunately, this was one of Steve Wozniak's main strengths. He designed the video circuit for the breakout game at Atari before starting Apple with Steve Jobs. The circuit handles both text and graphics modes, but for now I'm going to concentrate on the high-res graphics mode, and that's because I want to see Pac-Man working. The high-res graphics mode is essentially a 280 by 192 bitmap pixel display, but Steve Wozniak was able to use some NTSC trickery to generate a 140 by 192 display which had colour. But of particular importance is the way that the memory was fetched. The sweep pattern through the memory kept the dynamic memory refreshed, which was important because the 6502 didn't automatically refresh dynamic memories. In this build we use static RAMs, so it's not really an issue. The Apple II monitor and television displays of the time were based on cathode ray tubes, or CRTs. Here's a cross-section of a CRT. At the back is an electron gun, which produces free electrons. These electrons are accelerated towards the front of the screen. The front of the screen is coated with phosphor, and when these electrons hit the phosphor, they glow various colours depending on the nature of the phosphor. At the side of the tube, we have these deflector coils, and these would generate a magnetic field which could bend the electron beam. By using two sets, we could bend the beam from left to right and top to bottom. So using some clever electronics, we would sweep the beam, starting at the top left, go from left to right, sweep back and down a little, and then repeat. And eventually we'd produce an image one line at a time. This pattern of scanning is called a raster scan. So if we control the electron gun and the deflector magnets, then we can generate an image. Here we sweep from left to right. Once we get to the far right of the screen, we quickly scan back to the left and down a little. Then we start a new line. The individual dots, or pixels, are aligned to the dot clock. Eventually, we repeat this from top to bottom to generate the entire picture. Here we're making the Apple II logo. This is a single character, which is 7 pixels wide and 8 lines high. Now let's go into a little bit more detail about the different modes. There's the text mode, which displays 40 by 24 characters, a low-resolution graphics mode, which is 40 by 48 pixels with 16 colours, a high-resolution monochrome mode, which is 280 by 192 pixels, and finally a high-resolution colour mode, which is 140 by 192 pixels. And colour generation is a little complex, so we'll come back to that later. There's also a mixed mode which combines text and high-resolution graphics. For now, I'm going to focus mainly on high-res mode to get Pac-Man working. NTSC is the national television standard defined in 1941, and we need to understand how this works to be able to generate an image to display on a television from that era. Colour was added in 1954, and this format was used in North America until 2009. Formally, it's defined as having 525 lines at 30 frames per second, and it uses a really annoying interlace pattern. Fortunately, it also works at 262 lines at 60 frames per second progressive, which is what the Apple uses. Both 30 and 60 frames per second are actually higher than the flicker fusion rate, which is the rate at which images appear to merge to form an animation. But these numbers were chosen to match the 60 Hz mains electricity supply. Otherwise, if you don't have good filtering on the mains power supply, you get an annoying beating pattern on the display. NTSC uses a colour reference signal of 3.579545 MHz, and we'll see how this is important for defining the Apple main clock later. Now, many builds out there on the internet will use the VGA standard, and VGA is defined as 640 by 480 active pixels at 60 frames per second. But what it really is, it's 525 lines at 60 frames per second, versus the 525 lines at 30 frames per second for NTSC. It requires a pixel clock of 25.175 MHz, but if you downscale the resolution you can get away with much lower clock frequencies. From a build perspective, the real advantage of VGA is it's much easier to generate colour. It has 3 separate signals, R, G and B, which are independent, and the voltage on these signals determines the colour on the display at that time. HSYNC and VSync are separate signals, which makes that easier as well. And I was actually thinking about using VGA for this build, but eventually decided to generate a composite NTSC signal, which is the same as the Apple II. And the reason for this is that composite input signals are still very common on many TVs, but regular VGA inputs are getting harder to find, and some monitors don't even support the old 640 by 480 resolution mode. So remember that the display generates one scan line at a time, and the image is made up of several scan lines. This is the format the Apple II uses to generate each scan line. There are 65 characters, each 7 pixels wide, except for one character which is 8 pixels wide. But we won't worry about that for now. We'll just treat each character as being 7 pixels wide. We will have to address this though when we try and generate colour. The first 40 characters are for active display, and this is the text and graphics that we see on the screen. After the active area is a blank region, and a signal called horizontal sync occurs halfway through the blank region. Now this is meant to be approximately 5 characters wide, and it tells the monitor or TV to scan from the far right back to the far left. The regions immediately before and after the sync signal are called the front and back porches respectively, which I personally think is bass awkward, but I didn't get a say. The timing for these signals are determined by the NTSC standard, and so in reality they're a little arbitrary, but if you want to display something on a monitor of the time, you have to use these signals. The Apple II uses a multiple of the 3.579545 MHz color burst signal in NTSC. Specifically, the clock is 4 times this, so the primary Apple II clock is 14.318 MHz. And I think the primary reason for doing this is that it helps generate color in NTSC. We need to divide this 14 MHz signal by 2 to get the dot clock, so the dot clock is approximately 7 MHz, and we need to divide the 14 MHz signal by 14 to get the character clock, so the character clock rate is approximately 1 MHz. Thus, we have 7 dot clocks per character clock. Now fortunately, crystal oscillators at this frequency are cheap and commonly available. The first thing I need to do is generate a clock signal from this 14.318 MHz crystal. Now I've been using this clock circuit for over 30 years, and to be honest, I'm not quite sure who the original designer was. But it consists of 2 inverters, with a 1K resistor connected between the input and the output of each inverter. The output of one inverter is connected to the input of the other inverter via our 100 nanofarad capacitor. A small capacitor to ground is used to help start the circuit. And the alternate input and output are connected via the crystal. Now we have a square wave, which is 70 nanoseconds wide, which is exactly what we need for 14 MHz. The reason I use this clock circuit is it just works every time. Now that we've got the clock working, we need to divide the signal to generate our dot clock and our character clock. To help with this, I'm going to introduce the 74HC393 counter. This is a little different than the circuit used in the Apple II, but this design is just to illustrate a point, and I wanted to keep it simple. Normally the 74HC393 counts from 0 to 15, then back to 0. Here are the binary numbers associated with all the output values. Q0 is the least significant bit, while Q3 is the most significant bit, and this is a convention we use to define the ordering of the output. And there are 2 counters in each physical chip. Now let's try and generate the dot clock and the character clock. First I connect the clock, and I want to divide it by 2 to get the dot clock. That's pretty straightforward, that's just the least significant bit of the counter. And the dot clock is sometimes called the pixel clock. After dividing it by 2, I want to further divide it by 7 to get the character clock. This 7 represents the 7 pixels per character. 2 times 7 is 14, so I want the 74HC393 to count from 0 to 13, not from 0 to 15. I can achieve this by connecting an AND gate to the upper 3 bits of the counter and feeding the output of the AND gate back into the reset. Now unfortunately, when we draw these counters, we tend to draw the most significant bit on the right and the least significant bit on the left. So the bit pattern is actually reversed. That means we really need to read the output from right to left. The 0111 is actually 1110, which is 0E in hexadecimal, which is equal to 14 decimal. So the circuit counts 0 through 13. Then, when it gets to 14, all of the inputs on the AND gate are high, the output goes high, and this resets the counter. The counter then goes back to 0. So within that 1 clock cycle, it'll be 14 for a very short period, then 0 for the rest of the clock cycle. Alright, let's build and test this circuit. And instead of one single 3-input AND gate, I'm going to use a set of 2-input AND gates. We can see that this is 10 divisions wide at 100 nanoseconds per division, so it's approximately a microsecond. But we note that it's asymmetric. It's low for 550 nanoseconds and high for 450 nanoseconds. And this corresponds to the 8 clock cycles it's low and the 6 clock cycles it's high. One of the features of the 74HC393 is that it can be cascaded. That means we can connect multiple counters together. Here we connect the most significant bit of the upper counter to the clock pulse of the lower counter, and we end up with an 8-bit counter. For this to work though, we also need to combine the resets. And this is a really useful feature, because the next thing I want to do is count out the 65 characters on a Scanline. Here we can see our original counter on the left. I take its most significant bit and use it as clock for a new counter. In fact, this is our character clock signal. And on the right, I've connected two counters together to form an 8-bit counter, although I'm only showing 7 bits here. So how do I divide by 65? I wait until the pattern 1000001 appears, which I can detect with a simple 2-input AND gate. This signal then resets the counter, and the number 65 goes back to being 0. So this counter counts 0 through 64. Let's instantiate these counters and hook up the AND gate. So this signals HC6, which is also line count. It should be high for one character. Now we can see the signals are about 64 microseconds apart, which is correct. When we zoom in, we can see that the signal is about 1 microsecond wide, which is correct. So I'm happy that this part of the circuit's working so far. Remember that this breadboard design is just to demonstrate the concepts. I'm going to do it quite differently for the wire-by-wire build. Now if we go back to our Scanline representation, we can see this horizontal sync signal, which is supposed to be 4.85 microseconds wide, and this is derived from the NTSC standard. Given that each character is just under 1 microsecond wide, this is approximately 5 characters wide. But most televisions and monitors aren't super strict about this, so I'm going to see if I can get away with 4. So I want a signal that's low at the start of the Scanline, becomes high at character 48, stays high until character 51, and then at character 52 goes low again, and stays low until the end of the Scanline. This is our actual horizontal sync, or HSYNC signal. And here's the logic circuit I'm going to use to do that. It's a 4-input AND gate, until the inputs are inverted. When the middle bits are set to 1100, will be between 48 and 51 inclusive. So this is our horizontal sync signal. It's not as clean as the other signal and the scope's having trouble locking onto it. I'll freeze it on a single frame. It looks about 64 microseconds apart and the signals look about 4 microseconds wide, so that looks correct. But there's no way I'm going to try and use that signal for HSYNC. The problem is that after the edge of the clock, the output from the counters is actually invalid. It takes another 10 or 20 nanoseconds for the outputs to settle and become valid. So these spikes are the result of rubbish on the output pins of the counters. What I need to do is sample the signal when it is valid. And for this, I'm going to need another flip-flop. In fact, I'm going to sample HSYNC on the opposite edge of the clock. That'll give the counter outputs plenty of time to settle. I'm going to use this chip, a 74HC174 for the flip-flop. It's a hex flip-flop. It's very similar to the 74HC273, except it only has 6 flip-flops instead of 8. And the reason I'm using this is in case there are some other signals I need to clean up. This will move the image by half a pixel to the left, but I'm not really worried about that at this stage. So this is the sort of clean signal I want to send to the monitor, and it's occurring every 64 microseconds. Looks about 4 microseconds wide, so this is looking good. So we've gone over the horizontal counters and generated a horizontal sync signal, so that's the end of this video. Next video we'll move on to the vertical counters and vertical sync. And remember, like, subscribe, share.